Thank you, Stephen. Also, thank you, the organizer, to give me this opportunity to visit Manchester again. I say all this, say a few words, but really my words are very short, in the sense of I first met Nick when we are on the shuttle bus to Tennessee, attending the Household Meeting 10. So he's very noticeably in the sense of his alarm clock went off during our shuttle bus, and drive this taxi driver crazy. And I figured out, we searched all the bag. Finally, is Nick responsible for that? We stopped on the highway, etc. But of course, since then, here it's a quotation I cited from this household meeting. Also later changed the name on that meeting called the Gatlinburg 10. So when we asked what they have been most impressed about the meetings, and many participants, were quickly to cite the presentation by Nick Hine. This is also he won a household prize on that year. The rest, I think, it's all just a history in the sense of that. I think already has a lot of things to say about Nick in this morning session. I'm sure there's more is coming in the rest of talks, and also tomorrow Nick will be on the grill for a couple of days on that. But probably many things you can say about Nick. I think the other thing of this Sven, it's already say that Nick is really an ambient. I really rating him as a professional levels of that. So this is his own self-portrait. Okay, I cannot have a skill take that picture of him when we take an escalator in one of the higher rise in the building, and Nick captured the moment himself, but literally he wanted to take to me, but really I shadowed myself. So I specially portrayed this once, and also got some friend a secret signature on the back. So Nick, this is my gift to you. Yeah. It's yourself of that. I really love that. Of course, there's a hidden pressure. This is me. You see, I wrote it on that. Yeah, the rest is I say really appreciate all those 35 plus years of friendship. And also other things you also should notice that Nick wrote this mathematical writing. So he did not mention that explicitly. All this bad practice example is from me. Oh, you too? No. I'm more responsible, probably motivated Nick to write a book, teach us all this stuff. Because particularly in 1992, we spent 6 months together in Minnesota, this IMA. So we, literally for lunch and dinner, we just find a place and also everything I wrote, ask Nick to give me the correction, etc. So he inspired that book, all the examples I am responsible for. So of course, I continue making that up to today. So it feels very bad. All right, for the rest of talk, a little technical in a sense that there's quite a bit formula, migratory, excuse me. So I'm talking about a nonlinear eigenvalue problems, which is quite a popular, particular Manchester team instead of the earlier days of Nick and a friend did quite a bit, and until most recently, Stefan and Nick wrote a beautiful survey for a nonlinear eigenvalue problem. But that types is the matrices here is distinguished, is the matrices I'm considering here is depend on the eigenvector you wanted to find it. Instead of typically the nonlinear eigenvalue problems is the H matrices here depend on the eigenvalues. So in other words, differentiate those two different types of nonlinearity. I put a little V now today. The common notation is already accepted by community. Put a little V back just to distinguish nonlinear eigenvalue problem, depend on the eigenvalue or depend on the eigenvector. So this is I wanted to give you the next over 20 minutes or so, give you a little bit of a quick overview the development, mostly in the last couple of years in this. So here we assume this H matrices is invariance regarding your eigenvectors of that. So in this case, because in this case we can define the so-called uniqueness, or you're really looking for the subspace, etc. Of course, this eigenvector eigenvalue matrices, which is a capital lambda here, It's typically assuming is the matrices, because for simple, we assume is a Hermitian. So therefore, the lambda is the symmetric and have the Hermitian matrices. So it has the eigenvalue, typically associated with the largest or smallest. But of course, you can also classify in other sense. So where are those problems coming from? So you might wonder. Of course, the most famous ones is from the electronic structure calculation, or today in general, people call it computational material science. So this is the simplest example you can look at it. So in this case, the matrices depend on this rule vector. This rule vector is the so-called charge densities of electrons. So therefore, it depends on the eigenvector you're looking at. So L here typically depend on kinetic energy. So therefore, you can think about it as Laplacian or something like that. So this is clearly a matrices depend on the eigenvector you are looking for. Of course, in the reality, the matrices HV as Hamiltonian is much more involved in including all sort of other different type of energy, etc. For most, probably the most difficulty to model is the last term. It's over there is called exchange correlation energies, which really depend on particular physics, different physics study, propose the different models, etc. Okay, so I will say more of that later. Of course, besides this very well-known and most very intensive study, turn out this type of nonlinear eigenvalue problems arising from many other settings. For example, most well-known one of example is linear discriminant analysis. So if you only do single one-dimensional of that, of course, we all know this is just the standard Rayleigh quotient, which is equivalent to eigenvalue problems of so the denominator and numerator matrices. But of course, typically, if you want to do higher dimensional, you want a projection of this instead of one dimension, you do the k dimension. So you need to solve this so-called trace ratio optimization problem. It turned out this is not my work or our work, but a few years ago, this is already realizing. In this case, the global optimal is equivalent to find the eigenvectors of this nonlinear eigenvalue problems of that. So this is very well understood and regularly be able to prove. Of course, today, this model has been extended quite a bit general. For example, so this is typically we call this is a two view, assuming you have two data has two different cluster, only single view. But if you do multiple people call it multi-view learning, etc. In the same data set, you can have a different way of sampling those. So you will reduce to so-called trace of those, a sum of those trace of those. So this turned out is also equivalent to a nonlinear eigenvalue problems like that. Or more recently, some of you already heard of this so-called optimum transport distance, also called a Wasserstein distance. And you do this type of a nonlinear the dimensional reduction is also reduced to this type of that. The another example, for example, in data uncertainty modeling. So when you're collecting the data, you want to take into account of certain components of that may be subject to certain uncertainties or subject to certain noise. So in our case, just like previously to doing the discriminant analysis, so you need to take into account of those matrices has certain uncertainty data. So therefore, you are typical the discriminant analysis will be depend on those matrices, depend on certain parameter. Within a proper assumption, you can see this will be reduced to a province, which in this case, both matrices, coefficient and denominator and matrices, both going to be depend on these so-called eigenvector you are looking for. Okay. So it turned out equivalent can be doing it. So this type of the analysis also has a term so-called robust Fisher discriminant analysis. It was promoted by the Steve Boyd, etc., a few years ago. But more recently, for example, one of my students right now working on the BCI brain-computer interface system. So we're doing this so-called common spatial pattern analysis to extracting the EEG signal from brain imaging. So it turned out out exactly turn to solving this type of nonlinear eigenvalue problems. Here is just a simple example to illustrating the, if you do not taking care of the data uncertainty, those are the clustering point. So therefore, this will be the cluster to separate one cluster to the other. But if you're taking apart this particular data you collected, I should excuse me on this side of that, then you take into the data uncertainty, as you can see, the classify code changes significantly. So this is basically of that. Okay, so this is a three example to demonstrate from different setting how this type of that. Here is just an incomplete list of publication just in the last 2 years or less, and published on this nonlinear eigenvalue problem. In fact, last week, we just had one PhD thesis. I was on the thesis committee from the KU Riven, Carl Milberg, and the student defended his thesis on this topic exactly, because the thesis hasn't published formally passed yet. So that's why I'm not exactly quote here. But anyway, I hopefully I lay out, it's a very clear, this is very interesting and a very lots of application arising from the material science and also from the data science and machine learning these days. Okay, so what's the development, particularly in the last couple of years? So I roughly organizing in this 4 part. First is about basic theory, and the next is about algorithms. And then, of course, the algorithm among most of them, one of the we call the gateway method, just like a power method for linear eigenvalue problems. The gateway method to solve this type of eigenvalue problem is called SCF, stands for self-consistent field iteration. So in this case, it will be, I will focusing on that. And if time's along, I will go to the 2 application, a little bit more detail, but if not, I just can just safely skip. So this has been the of work in the last 10 years or so. I really get into this field is working with the electronic structure people. So we try to integrate our eigensolver into their package at the Lawrence Livermore lab. So afterwards, I had a chance to work in people with a bunch of the group at a different of that. So I feel those are the people, and I had with them in the last had some publication with them in the last few years. So first is about theory. What do we know about this nonlinear eigenvalue problems? So here is the results about existence and the uniqueness. So uniqueness is an assumption is a subspace invariance property, etc. Okay, so it turned out is that if you're making the assumption basically about Lipschitz-like condition about matrices, okay, so this is the A1 assumption. If you have some Lipschitz type of assumptions, and also you have this so-called universal gap among the eigenvector space versus the rest, and you can rigorously prove for such types of nonlinear eigenvalue problems, the solution exists and unique. Okay, so this in certain sense, of course, how to verify the first property probably is most harder to verify in practice. So Lipschitz type of condition, how you, if the Hamiltonian or this matrix is too evolved. The second one typically is from given the problems, the property itself in the electronic structure. Typically, we're realizing this uniform, the gap assumption, this existing uniform, that this delta is dependent on the material. For example, for metallic systems, so this delta essentially goes to 0. So therefore, this assumption is questionable. But from our linear algebra point of view, this is very, in a certain sense, assuring about the problems in what sense it can be well defined or practically solvable. So here is an example to show is the use of such a theory in electronic structure calculation. As I say, in the reality, the matrices involved there, are quite evolved. But it turned out is really, it's only the exchange correlation terms is going to determine of the essential properties about this nonlinear eigenvalue problems. Of course, the universal bound is still needed. I should write it down there. Yeah, this is still needed. Okay, you need to have a universal bound, and also the more critically is the exchange correlation terms. Of course, exchange correlation in the real physics is most harder to get. So a very different physicists you talk to them. There is a whole website collecting all these different electronic correlation terms people have been studied, and it's very hard to come up a uniform definition, etc. So that's one of the push we try to do in that application venue. There is quite a bit of recent advances and regarding this theoretical aspect. For example, regarding the sensitivities of this type of eigenvalue problems, I would call it is a perturbation theory labeled in. Also, there's of course in eigenvalue problems, it's like Peloponnese norms, a theory, etc., are very fundamentally understanding of eigenvector structure and how they will be used in practice, etc. So there's quite a bit also interested development. But overall, it's relatively scary in this field about theoretical aspect of that. Okay, so this is overall I wanted to say about the development in theoretical aspect. So algorithmically, there's quite a bit of a common suspect, you might call it, once you hit this. So here it's a few of that. So started with the self-consistent of that because the electronic structure like Hartree formula, etc., is already studied in the 30s and 40s, and this is so-called self-consistent field iteration already invented, even probably along the like a power method, etc. But more recently, electronic structures struggle within the SCF, the issues, and they come up lots of variants and a different definition. It's a huge list of that. If you're interested, I'll quoted a survey article, but it's still a few years old. But more recently, because of some of the numerical linear algebra people like me get into that field, so we look into other alternative methods, such as the power method and such also Newton's method, and most recently, even try to extend it so-called a counter integral method to this. As you can see, inevitably, those methods are going to be more and more evolved because for general nonlinear eigenvalue dependent eigenvalue only, it's already very evolved. It's already very messy. How messy this will get to, but nevertheless. For the rest of talk, I will focusing on this SCF. So SCF is very simple. It's basically say because your H matrix depend on the eigenvector, so I don't know what that is. So I just fix that H matrices first, and then I solve linear eigenvalue problem. So therefore, this method is just although I wrote a few lines here, it's really literally just one line. So every time you just solve this linear eigenvalue problems iteratively. So therefore, this method is also known is called iterative diagonalization. Basically, you try to make H's the coefficients matrix become a diagonal or partial diagonal. You do that iteratively. Or the other name also people call the linear eigenvalue problems with evolving the matrices. This Joseph Sader like to using this term. So in this case, you are solving a sequence of the linear eigenvalue problems, but every time you come back, this matrices A is changed a little bit. So therefore, what's this method of that? Of course, so here is you might wonder why we wanted to do this. Okay, so if some of them, if you can directly solve, and why you want to convert it to a nonlinear eigenvalue problems and then solve them. So let me using this simple example of a linear discriminant analysis as an example. So in this case, as you can see, I already say it's can be equivalent to solve this nonlinear eigenvalue problems. But of course, for this method, as you can see, it's a standard of optimization method on a manifold. Today, we have quite a bit of good understanding of how to solve this method optimization problem directly. So therefore, here I list the three methods. First is before this manifold type of method is people try to solving this nonlinear eigenvalue problems or this trace ratio is by you just using generalizing the eigenvalue method. So today let's call it heuristics method because this is not exactly solving this, but solving the problems very closely. Alternatively, you can use this orthogonalization on the manifold. So this is called a steeple manifold trust ranging method, which is a package that we used. The third, of course, I can using the nonlinear eigenvalue problems using the SCF to do this. So here is the so-called toy problems. It shows you original 3 data set. So if you're using these heuristically, you're completely losing the data, the structure essence. But using the other two methods, you can get a very clear, a good, decent separation about the original cluster, etc. But the difference is in the timing. If you use the optimization method, as it grows very rapidly within the dimensionality. But of course, we know that a linear eigensolver is very scalable in that sense. But nevertheless, using this green lines, this is of this new of that. And it's really as scalable as the original of that. So this is hopefully convincing you that do have a benefit to using this method to do this. Of course, reality is more complicated. So this is one of the results we did for electronic structure calculation published on the Journal of Computational Physics. As you can see, it's never going to be very smooth, juggling, etc. So there's a lot of trick to resolve that issue. One of recent work is interesting is to push some geometrical, so-called geometrical understanding of this SCF. So we particularly looking at a certain type of the nonlinear eigenvalue problems of that. But in this case, the matrices here is not a dependent, is a dependent eigenvector, but a particular dependent on the so-called really Gaussian types of that. Because in this case, you can use SCF, very easy to solve. But it turned out is that you can rigorously prove under very weak assumption this type of SCF has the so-called of global convergence. But more important, this has a lot of interesting applications for these types. But let me skip that. More interesting is you can have some variational form for such nonlinear eigenvalue problems. So this is a very sort of desirable when you deal with eigenvalue problems. But furthermore, is you can rewriting this in terms of on the so-called joint matrix range of that. And within this, you can interpolate SCF exactly using geometrically how it may be just using the picture, this formula too long. So you can think about it, you are trying to optimizing in this so-called joint numerical range. So every time you're doing the search, once you after studying, you search for the optimal in around the edge. Of course, here is a circle, there's no exactly edge per se. But nevertheless, you can exactly define the normal direction of the high plane and the search direction. And once the normal direction, search direction overlap, you know this, you find optimal solutions, etc. So this is a kind of a very interesting of geometrical interpretation, sort of try to mimic like a simplex method for LP types of thing motivated by that setting. Okay, so this is basically of that. The other is lots of understanding regarding the so-called convergence. So I'm finishing up in that, probably I will skip it. So this is the nonlinear. We're just looking at, for example, here is alpha is one of the parameters here, alpha. So as you can see, once the alpha is small, in other words, nonlinear term is not very strong, the convergence very rapidly. But once alpha getting larger and larger, and then the nonlinearity getting stronger and stronger, SCF will fail to converging. So that times this paper, Yang and Huang Mesa, etc., they're proposing this sort of little open problems, say how to find an optimal estimate of this alpha. Where is the sort of a breaking point, the alpha making this convergence, regardless how to slow, or non-convergence. So you kind of guess it's between the 0.85 and the 0.9. So therefore, what's the theory or what will be our understanding about this SCF? How can you predict what's the exactly turning point on that? So it turned out it's not a very trivial task. Here is a bunch of the paper and all the different theory being developed. And a couple of years ago, we wrote also paper itself and try to claim we get a good estimate, but never really to a level of satisfactory we have. But eventually, I think I can safely tell you today is our accuracy or understanding is very good. So this is the best results from the published previously publications. But now is we can sharply like at 0.5. So we can estimate between the observed and the theoretical, and we are off by 1 or 2% of the estimation. So this is we are finding is a very. But anyway, so I can say more about what's the implication of such convergence analysis to other application problems, etc. Okay. finally, the application I wanted to say, one thing is about orthogonal, the CCA is another commonly too. But today is people, instead of looking at this CCA in normal orthogonality, they want to directly looking for the projection subspace to be orthogonal by itself. It turned out that this is the province can turn it into a nonlinear eigenvector province. But more critically is this so-called multi-view of CCA, because it's data collecting today is quite abundant. So really you can have the same of analysis, same cluster with different view, etc. So this is certainly for directly try to treating such problems by using of linear algebra, traditional linear algebra, or optimization is very challenging. But we just published in IEEE pattern recognition and a method how to do this in a nonlinear eigenvector. And the other, for example, tensor approximation is another very interesting value. Of course, this type of thing is closely connecting to the optimization. So that's personally, my professional career is benefited enormously. I have been, very blessed in terms of people like, today celebrating the Nick, but earlier, like I was a postdoc Jack, and then know Margaret when I was literally as a junior student. So I kind of being exposed to all those different fields. I feel very grateful to overall my professional career, how it's being developed. Like this type of a problems, we probably never dare to, as quadratic optimization. That's not a linear algebra people do, isn't it? But turn out because natural this type of application, we're probably never going to touch them. But nevertheless, it's very inspiring, and turn out all this has a nice connection. Okay, so yeah, so I think my time is up. So really, I wanted to say it's a very relatively new. It's not a new relatively it's per se, but it's just to see the last publication in the last few years are very encouraging and exciting, and we do have a good understanding of quite a bit about this province and about some basic theory. But of course, nevertheless, there's a lot of enormous particular solver aspect. I think that's certainly very demanding. Steve, I'm looking at that. Hopefully I'm doing okay in timing. Okay, all right. Thank you, guys.